and S charts. Okay, you will use Minitab software to construct the control charts, and then we will make an analysis. Okay, and then we will put the results of our analysis in this table. Okay, we will do this right after we finish the lecture about control charts. Okay, so in the first part of the lecture today, we will finish the PowerPoint slide, okay, from last week. Okay. Okay, start with this slide on page 11. Okay, from last time we have learned that there are many types of control charts, right? And let me get the pointer first. Okay, the first group is variable control charts, and the second group is the control charts related to attribute data. Okay, for variable data, we will learn 3 types of charts in this course, which is highlighted as yellow here. Okay, X bar and R charts, X bar and S and IMR charts. Okay, and then yeah, we have finished the details of these 3 charts, right? We learned about how to calculate the control limits. Okay, and today we will practice on how to interpret the pattern that we see on the control charts. And okay, in last week we started looking at P charts, right? Okay, and then we still have these 3 charts left for today in P, C, and U charts. Okay, so I will move to the slide about P charts. Okay, which is on page 80. Okay, let's review about important terms a little bit, okay, before we move to the details of the calculation. Remember this picture? This picture gives you, okay, the ideas about the difference about defect and defective and how they are related. Okay, so one more time, okay, a defective or rejected part is a part that contains at least one defect, okay, and defect can be of any type, okay, like in this example, there are 4 types of defects that can happen, okay, on the cassette workpiece, okay, cracks, holes, flash, and breakouts. Okay, so for each part, it can contain no defect. Okay, that means it's not a defective. Okay, but if it contains, if it contains one defect, like in the first piece here, okay, this piece is also called a defective with one defect. The second piece, okay, is also a defective, and it contains 3 defects. The third piece is a defective also because it contains 1 defect. Part number 5, it contains no defect, so it's called a non-defective part, or you can say it's not a defective. Okay, so if you clearly understand about this, okay, we can move on to 4 types of control charts. Last time we talked about P chart, right? So P chart is the chart that monitor the defective rate. We can also call defective as non-conforming unit. Okay, so this chart control or monitor the fraction of non-conforming units. Okay, or you can say it monitor the defective rate or the proportion of defective. Okay, we can call it like several names, but it means the same thing. An NP chart, it monitors the number of non-conforming units in a sample, okay, that you collect. Okay, we will take a look at the example, okay, later. C charts, I'm sorry. Okay, C chart monitors the number of nonconformities or the number of defects, okay, in the parts that we sample, okay, and U charts monitors an average number of defects, okay, per 1 unit, okay, that we produce. Okay, so C and U charts monitor the number of defects, okay, not defective parts, but P and NP, it monitor or express the performance of our process in terms of the number of defective parts. Okay, you can distinguish about this, okay, clearer after we take a look at the examples. Okay, now let's review an example of P chart a little bit. Okay, take a look at this data table. So for each sample, in this case, there are 30 sample. Okay, 1 to 16 and 17 to 30 here. Okay, for each sample, or we can call it subgroup, contains, actually they contain, for each subgroup, they contains 50 cans or 50 parts, okay? And then we count the number of defective parts out of 50 parts that we sample for each sample, okay? And each sample, actually, first we have to determine the sampling frequency first. For example, we will do sampling every hour, okay? So 1 hour is our sampling frequency, okay? But in some situation, the change in the process happen pretty frequently, okay? More frequently than 1 hour. For example, if it can happen like every half an hour, we have to take a sample every half an hour. But okay, in some situation, the process is pretty stable, okay, and the abnormality or the mean change or the variation change can it usually happen for example, every 8 hours. So we can lengthen the sampling frequency, and then we can take sample every 8 hours instead of 1 hour, okay, to save the sampling time and cost. Okay, so for each sample mean the parts that we sample, okay, according to the sampling frequency that we determine. Okay, and okay, let's come back here. So for each hour, in this case, suppose they do sampling every half an hour. Okay, and for each half hour, they collect 50 cans, and then they inspect for and look for defects on each part, okay? And for sample number 1, they found 12 cans that are defective, okay? So out of 12 out of 50, it corresponds to the proportion of defective, which is 0.24, okay? In the second sample, 50 cans, they found 15 cans, okay? And then they convert to the defective rate, which is 15 over 50, which is about 0.3, okay? So do this for all samples, okay? And then if we average the defective rate, okay, over 30 samples, we will get what we call P bar, okay, which express an average of the proportion of defective, which is, which is 0.23, okay, roughly 20%, okay, of the parts that we produce, okay, they are like defective. Okay, next, we can calculate the control limits, okay, based on P bar and N. Okay, actually the control limits for defective rate is very easy. We need only two parameters. The first one is P bar, right? The first one is P bar. You see P bar here, here, and here. Okay, and the second one is sample size. In this case, we have constant sample size, which is 50. Constant mean constant over all samples. Okay, so for each sample, we sample 50 cans. Okay, so the sample size is constant, which is 50. Okay, so now we can plug in, okay, P bar and N, okay, and calculate the control limits. And also the center line CL here means center line, which is P bar, okay. And last time I talked about the proof of the control limits, okay. So we will skip this. And for P charts, okay, we have to make sure that the data collection correspond, okay, our data correspond or meet with these three assumptions. Okay, the first assumption is that N, or sample size that we collect in each sample, has to be at least 30 parts. In this case, we have 50, right, which is greater than 30. So the first assumption is met. The second assumption is this one. Okay, after we have calculated the defective rate, in this case, P bar is equal to 0.23, right? Okay, let me get a pen first. Okay, in this case, P bar is 0.23. Okay, and then N is 50, right? So the multiplication of these two numbers is about 11. Okay, roughly it's about 11. So 11 is greater than 5, right? So the second assumption is met. And the third assumption is the multiplication of N and 1 minus P bar, okay, which is about 50 times, right, okay, which is roughly, okay, about 38, which is greater than 5, right? So the third assumption is met, okay? So in this case, okay, all three assumptions are met. So that means we can approximate, okay, the binomial distribution with the normal distribution. Binomial distribution because the number of defectives, okay, in this case, out of 50 cans, actually it has binomial distribution, but the formula to calculate the control limit here, okay, is based on normal assumption because 3 here is the z value, the standard normal variable, okay. So we assume that the statistics that we plot on the control charts, in this case is the proportion of defective, is normally distributed, okay, before we can use this, so that we can use this equation. Okay, so then we have to make sure that the proportion of defective is normally distributed, okay, but P in this case come from the number of defective over sample size, and we start with the binomial distribution for D. Okay, the number of defective. Actually, its original distribution is binomial. Okay, so if P, okay, if our data, okay, correspond to these three assumptions, okay, the binomial distribution can be approximated by a normal distribution also. Okay, so that means we can use this formula, okay, if those three assumptions are met. Okay, and in this case, the three assumptions are met, so we can continue to use this formula, okay, to calculate the control limits for P chart. Okay, so next step, we can calculate the control limits, okay, using the formula that we have seen before. Okay, we just plug in P bar plus 3, P bar 1 minus P bar, and this is N. Okay, and then we can get the first set of the control limits. Okay, so the first set or the first round of the control limits, we call it as a trial control limits. Trial means we have to try it first. It may not be a final control limits that we can use. Okay, because we have to check for something before we finalize with the control limits. Okay, the things that we have to check is that are all the samples come from the process which is in the control state. Like in this case, there are 2 points or 2 subgroups that the defective rates are significantly high, okay, higher than the upper control limit. This is the upper control limits, right? So if these 2 subgroups has significantly high value, that means we have to think that there may be something wrong with the process. There may be special cause happen during these 2 hours. Okay, so what we have to do is that, okay, we have to go back and investigate the causes of this abnormality. Okay, and then we found that for sample 15, okay, here 15 and 23, okay, for sample 15, a new batch of cardboard stock was put in the production process. Okay, and maybe the quality is poor. Okay, so it caused very high defective rates. Okay, and for sample 23, okay, an inexperienced worker can come and work in that process. Okay, so he or she may make some error. Okay, and after we have identified the special cause, okay, and do some preventive action, like in this case, if the abnormality happened from the poor quality of material, so what we have to do to prevent this error in the future is that we have to make sure that our inspection of the raw material is in good condition. So for example, we have to set up acceptance sampling plan like you have learned from Ajahn Damrong, right? So you have to make sure that your sampling plan is okay. Okay, it's good enough to detect an error or defective parts that will come into your process, right? And after you're sure that or improve your inspection plan, okay, already, so you're pretty sure that in the future this abnormality will not happen again. Okay, so that means in the future this high value will not appear, okay, in your process. Same thing for inexperienced worker. Okay, you will train the new operators to some standard, okay, and make sure that the operators understand how to work in the future before you put he or she into the process. Okay, and if that happens, this high number will not appear in your process anymore. Okay, that's mean your process after this, okay, will have variation which is not this high, but it will, okay, corresponding to the variation which, okay, come from this 28 subgroup. Okay, we start with 30 subgroups, right? Okay, if we so now we should delete these two subgroups out of the calculation of the control limits, okay, and use only 28 subgroups, or what we call samples, in the calculation of the control limits, because we are pretty sure that this 28 samples come from the process which is in the state of control. Okay, so that's mean this is called the trial control limits, right? Okay, but after we delete two subgroups out of the control limits, we will get the second set of the control limits. Okay, I'm sorry. Okay, so the second set we can call revised control limits. Okay, and then we have to check again if there are still subgroups which is or are out of control. Like in this case, okay, first we delete this subgroup, right, and this subgroup out. Okay, and then after, take a look at this. UCL is equal to P bar plus 3. Okay, this equation. When P bar is reduced, okay, the control limit will be narrower, like before the first round or trial control limit may be at this point, okay, but after we revise P bar, okay, center line will change, upper control limit will be narrower, okay, to this point, and at this level of the new control limit, this point now become an extreme point, or the point which is out of control limit. Okay, and again we have to redo the process, okay, that we have done. That is, we have to check to find out the cause of this abnormality, okay, and then if we find it, and then we can do preventive action. Okay, we will delete this subgroup, okay, from our calculation, okay, in the second round, and then recalculate the control limits, okay, and then we will do this until all the points are within the control limits, okay, and then we will obtain what we call final control limits, okay, and in this example, okay, suppose we have deleted this point out, okay, and then we will obtain what we call final control limits, okay, and suppose the final control limit is here, okay, so now we obtain the final control limits, which are the control limits that calculated from the points that are in control or within the control limits, okay, and we will use those control limits, okay, to make interpretation of our process in the future. So that means in the future we have to collect more sample every half an hour, and then we have to plot the proportion of defective onto the final control charts, and then make the interpretation, okay, based on the rules that we will learn from the workshop today. Okay, and this slide shows you that if first, okay, we obtain the final control limits at this level, this UCL, and then this is LCL. The center line is here, okay, and this slide want to show you that the control limits, we should update it, okay, periodically based on or depending on the status of the process. Like if we do machine adjustment to reduce the proportion of defective from this level to this level, so our P bar change from this level to this level, okay, we improve the process to get less defective rate, right? That is what we want, okay, from the process. We want the minimum defective rate, right? So we have to do continuous improvement, okay, all the time to reduce the defective rate, okay? And if at some point we found a good or better work method, okay, in this example, we found a new adjustment of the machine, okay, to reduce the defective rate, and it works. The defective rate now reduced to this level. So we have to update the control limits again, because the control limits is based on or dependent on P bar, right? So UCL and LCL, okay, now should be updated to the new level, okay, based on new P bar. Okay, so in this slide, I want to show you that the control limit should be updated from time to time, okay, depending on the change in the P bar and also the change in the sample size. Remember that control limit is based on sample size also, right? So if right now we use sample size of 50, right? But in the future, if we increase the sample size to 70, for example, so we have to change the control limit, right? Because the control limit is based on sample size. We will get the narrower control limits if we increase the sample size. Okay, so this is the point that I want you to know. Okay, and about the interpretation of the pattern on P charts. Okay, so we will use only 4 tests. Okay, and we will learn about the test, okay, later in this class. So just remember that we can use 4 out of 8 tests. We cannot use all the tests, okay, and the reason I will tell you later. And last time we talked about 3 approaches or 3 methods to calculate the control limits, right? Okay, I will not, okay, explain this, okay, in the second time because we have learned about this. Okay, briefly, okay, revisit this. The first method is variable with control limits, because if sample size change over samples, the control limits, which is based on the sample size, should be changed also, right? Will be changed also. So we will get variable with control limits, which is not convenient for use. So if we want a stable or constant control limits, okay, so that means we have to use a constant sample size based on an average sample size, which we call n bar. So n bar is an average of all of sample size over m, or all samples that we have, right? And then we will plug in n bar in the calculation of the control limits, okay? And if you use this method, you have to be careful, okay, for the subgroup which is near the control limit, like in this, okay, at this sample. That means you have to recalculate the control limits of that sample based on the true or actual sample size of that sample. And suppose in this case, the new control limit, or actually the actual control limit, is at this level. So that means you have to conclude that this subgroup is out of control. But if you use the control limit based on n bar, you will make wrong conclusion, right? That that point is still within the control limits. So you will say that the process is still in control, but actually it's not. So you have to make sure that, okay, if you have the point near the control limit, it can be lower than the control limit or above the control limit. If it's above the control limits, you have to recalculate the actual control limit for that subgroup, and it can be at this point or at this level. And if that is the case, that means the conclusion based on the actual sample size, which is the correct conclusion, okay, may not be the same, or it can be different from the conclusion that you make based on the n bar, right? Okay, so that's why you have to pay attention to the points near the control limits. And the third method is standardized control charts. This is the best in terms of the quality of the conclusion. Okay, and we also have a constant control limit. Okay, because we will convert or transform the proportion of defective, okay, for each subgroup, okay, to the standard normal variable. Okay, we change from P to Z, okay, based on the actual sample size. So that means we have taken into account the actual sample size for each subgroup. That means we will make correct conclusion based or for each subgroups, and we can also have a constant, okay, control limit. So that this is the advantage, advantages of this method. Okay, like this. Okay, C variable. And next, we will move to another type of control chart, which is C chart. Okay. C chart is used to monitor the number of defects over the parts that we sample for each subgroup. Okay. The number of defects, okay, can happen in a given area. For example, you inspect the defect that happened on an area of metal sheet, okay, or cloth, okay, and in some situation, we want to monitor the number of defects in a volume, okay, of a part. For example, you make some, okay, glass cube like this, okay, or a casted workpiece, okay, and then you monitor the bubble, okay, in the glass cube, or you monitor the holes in your casted workpiece. Okay, so you want to count or monitor the number of defects over a volume of products. Okay, in this case, you can use C chart also. Okay, and sometimes you may want to monitor the number of error, okay, or the number of any kind of events, okay, over a time period. Okay, for example, you want to monitor the number of complaints of your customers, okay, about the service of hospital, or the number of complaints, okay, during about the use, okay, of any products that you sell. Okay, you set up, suppose you set up a call center to receive, okay, the number of complaints, or okay, any method that you, okay, collect the number of complaints, okay, during time interval. Okay, in that case, the number of complaints, okay, is, you can use C chart to monitor like this type of data. So in summary, if you want to monitor the number of events. Events here can be complaints, can be defects, okay, over area, volume, or time. Okay, the number of events is or has Poisson distribution. Remember Poisson distribution from statistics course. Okay, it used to represent the distribution of the numbers of events over time, volume, or area. Okay, and Poisson distribution contains one parameter which is called lambda. Actually, lambda is an average event rate. For example, let me see. Let's take a look at the example in this case. If we want to monitor the number of defects or nonconformities over 100 printed circuit board, okay, we can call this PCB. Okay, it's an electronics product. Okay, so for each subgroup, like for sample 1 or subgroup 1, okay, you inspect 100 PCBs, right? And then you count the number of defects that happen on those PCB. Remember that for each PCB, it can contain at least one defect. Okay, it can be 0 or 1 or 2. Okay, and there's no upper bound for the number of defects over each part. Okay, in theory, okay, there's no upper bound. Okay, and suppose, okay, you collect for sample number 1, you have part number 1, 2, 3, okay, until 100. Okay, and then you record the number of defects over each part. Okay, for example, part number 1, there's no defect, so the number of defect is 0. The second part, you found 2 defects, okay, and the third part, you found 1 defect, okay, 0, 3, things like this, okay, and then you sum up all the numbers, okay, and you may see that okay, you have got 21 defects over 100 parts that you sample. Okay, so this number is called C number. C stands for or represent the number of nonconformities over the parts that you sample in each subgroup. Okay, and then you will have 24 for the next 100 parts. Okay, right? And if you average, okay, the C number over 26 samples, you will get what we call C bar, okay, an average of the C number. And then we have this formula to calculate the control limits for C chart, okay. Center line is at C bar. U and LCL is mean, remember, plus 3 sigma, right? And mean in this case is C bar, okay? Sigma for the Poisson data is the square root of the mean, okay? So that's why we will have this formula for the calculation of the control limits. Okay. Go back a little bit, okay. Okay. So C chart usually, okay, it's necessary that we will use C charts when we have a constant sample size situation. That means for each subgroup we have all 100 parts, okay, and if the sample size is constant, so it's fair to plot the number of the number of defects, okay, for each subgroup. Like in this case, 21 here, 21, 24 here, because 21 and 24 come from the data or the number, the exact same number of parts, which is 100. Okay, but in case that you have different sample size, like in the case that you have 100 here, and then you have 120 parts in the second sample, 110, 90, okay. So if your sample size is not constant, so it's not fair to plot the C or the number of defects over unequal sample size, right? Okay. So if that is the case, we have to plot, or if we want to represent how many defects that we produce from our production process, we have to represent the number of defects over one unit instead. Okay, and one unit here doesn't mean 21 over 100. It necessarily means 24 over 120. Okay, you can specify what we call inspection unit. Okay, like here, one inspection unit, okay, can include several units. For example, one inspection unit can be equal to 3 square feet of cloth, or 4 glasses, okay, or like 10 parts. Okay. We will take a look in more detail when we use what we call U chart. So U chart is used for the case that you have non-constant sample size, okay, and then we will plot the number of defects over one inspection unit, okay. But C chart will use in the case where we have constant sample size, and then we plot the number of defects, okay, over any, okay, units, okay, that we do sampling, okay, but with one condition, that the number of units has to be equal for all subgroups. Okay, and now let's pay attention to C chart first. Okay, there is one assumption that you have to check when you use C chart. That assumption is that the C bar, okay, should be at least 10. Okay, that's mean. For example, in this case, after you record the C value for each sample, right, which is the number in this column, then you calculate let me see, calculate sorry, I don't have the numbers to show you. For example, if an average, okay, is C bar is equal to 20, okay, that means you meet with this assumption because your C bar is greater than 10. Is greater than 10. Now your C bar is 20, for example. Okay, so that means you can use this formula to calculate the control limits. Okay, so it will be, for example, C bar is equal to 20 plus 3 square root 20, and your center line is at 20. Your LCL is 20 minus 3 square root 20. Okay, and then you get the control limits. And then you can plot your control limits. Okay, the trial control limit first, right? And then you look for if there is extreme point, and yes, you have one extreme point that you found that is come from the abnormal temperature control. Okay, and then you make some preventive action, okay, to check your temperature in the future. And then after you can do your preventive action in the future. Okay, now for calculating control limits, you will delete this point out of your calculation like you do for P chart. Okay, after you delete this point, okay, then you have to calculate the revised control limit. Okay, suppose your revised control limit is at this point. Okay, and now you look for abnormal points again. And if you find that there's no points that are abnormal, okay, all the points are now within control. Okay, you will get the final control limits. Okay, that means you are done with the calculation of the control limits, and then you can use this set of control limit to monitor the process in the future. Okay, and then you will use 4 tests, okay, which is extreme point, run, train, cycle, okay, that you will learn, okay, in the later part of this class to monitor the abnormal pattern. Okay, next, okay, U-chart. Okay, U-chart is used in the case that you have non-constant sample size. Okay, so U is equal to C divided by N, right? Because U is number of defects over 1 inspection unit. N here mean the number of inspection units. Okay, and we have this formula to calculate the control limits. Okay, so same as the case for P charts. Okay, if N is not constant over samples, so we have to deal with the case of non-constant sample size like what we have for P chart. Okay, like take a look at this example first. If we inspect the quality, okay, of the cloth dyeing, okay, so we inspect in this case, like for example, we have 10 row of cloth, and for each row it has different areas. Like for row number 1, it contains 500 square meters of cloth. Okay, and over 500 square meters, we count the number of defects, okay, from related to the dyeing quality, and we've found 14 over 500 square meters. Okay, and next, okay, we define that one, okay, inspection unit, what we call inspection unit, is equal to 50 square meters of cloth. So 500 is equal to 500 divided by 50, okay, which is equal to 10 inspection units, right? And 400 divided by 50 is equal to 8 inspection units. Okay, so you do this for all subgroups, right? That means you convert this column into the column which is the number of inspection units. Okay, we reduce the number from 500 to 10. Okay, so that our U number here will be 14 over 10, okay, which is equal to 1.4. Okay, so this number will not be so small. Okay, we can have another choice, which is calculate U by 14 over 500, and then we will get a very small number, okay, which is more difficult to record or to show, okay, or to plot. Okay, so but actually it's not that very important. Okay, you can use to monitor or you use the calculate U number by the actual number of square meters, or you can convert it to the inspection unit first, before you calculating U number. Okay, it depends on you. Okay, so in this case, they reduced the number to inspection units, and then we will get this column, which is called U column, right? And then you average the numbers here, you will get what we call U bar, right? And then now we can start calculate the control limits with these three methods. Okay, so the first method is based on the actual sample size. Okay, so we have variable width of control limits like in this that you have seen before. The second method is based on average sample size. So you have to calculate n bar first and then plug it into the control limits formula, and then you will get constant control limits. And remember, like, to calculate the actual control limit for the point which is near, okay, the control limits. And the third method is standardized control charts. Like in the case of P charts, you use P, okay, and then standardize with actually with the mean of U. This is the mean of U, and then the standard deviation of U, which is this number, to get Z number before you plot on the control charts. So this is all like the materials, okay, related to the construction of the control limits for P, C, and U charts. Okay. So I think I will update the PowerPoint. Okay, that will show you actually there is another chart called NP. Okay, which is in the case it used in the case, okay, which is similar to P charts. You want to monitor the number of defective over the parts in a sample. Okay, but I'm not sure why like this slide it accidentally like removed the slides about NP charts calculation in this file. So okay, after this class, okay, in this afternoon I will update the slide for P charts, okay, and then please revisit, okay, the slide again. Okay, I will after I update the new file, okay, I will tell you in the line group, okay, and then please revisit the file again, okay, to get the formula to calculate the number of defective parts, okay, and by yourself. So if you have this background, okay, I think that you can follow, okay, the ideas about NP charts, not that difficult, okay. And actually, I think I will give you an example of the calculation based on the real number, okay. So let's wait for the new file, okay. So I'll give you the example of the calculation, okay, and also the formula to calculate NP charts, okay, later. Okay, so to summarize about the content of control charts, okay, before we move to the workshop, okay, compare between attribute control charts and variable control charts. Okay, so in the case that your quality characteristic is appearance, like you have to look for the numbers scratch on your product, okay, or bubble, or contamination, okay, this kind of things is called quality based on appearance. So it's certain that your data will be attribute data, and that is the case you have to use attribute control charts, which is depends on your situation. You can, if you want to monitor the defective, okay, defective, you will use P or NP. If you want to monitor the number of defects, you will use C or U. Okay. And if your data is variable data, okay, variable data, which is like the dimension of the parts, length, width, thickness, okay, those kind of thing. Okay. If your case is variable data, you should use variable control charts. Okay, and you have the choice to use X bar with R, X bar with S, or XMR. Okay, depends on the sample size or the situation of your production process, right? And in some case, okay, for in industry, okay, some people may convert the variable data into attribute data. Like for example, you have the length of the part, which is 12. Okay, and if they compare to the specification limits, your spec, suppose your spec is 9 to 11. Okay, and since 12 is greater than 11, so it will be a defective, right? So they convert this to, like, they will say this is a defective. If it's between this range, for example 10, okay, they will judge that this part is not a defective. 11.5, yes, is a defective. And then they convert, okay, the variable data to attribute data, okay, and then they count the number of defective. Suppose they have like 100 parts that they sample, okay, and then they found 10 parts that are defective. Okay, they will plot the number of defective, which is on the NP chart. Okay, and then they use NP chart instead of variable data control charts to monitor the process. Okay, but in this case, okay, I want you to know that you shouldn't do this approach. Okay, so if you have variable data, you should use X bar and S chart, okay, instead of converting it to whether it's defective or not and use NP charts. Okay, because variable data, okay, can give you more information. Okay, so you know about the mean of the process, the exact variation, numbers of your process. Okay, so if your case is variable data, that means you should use variable control charts instead of converting and use attribute control charts. Okay, that is the point for this slide. Okay. Okay, and then let's revisit this roadmap by yourself. Now you have learned all, okay, the charts here. Okay, in this class we deal with only the case for detecting large chip size. Remember that large chip size mean when your shift, or we can call your change in the process, it is, okay, greater than 1.5 times of the sigma, okay, of the process. Okay, and the guideline for implementing control charts is that, okay, first you have to determine which process you will monitor and which process characteristic. For example, the part, for some part, okay, there is what we call the main quality characteristic, okay, or the major characteristic. For example, if you make the part which looks like this, okay, the main or major characteristic is the dimension. It may be the height. Okay, so you have to decide whether you can you will monitor which dimension. Okay, in some product, okay, there are like hole here, okay, and in this case, suppose the whole dimension is very important, but the length, okay, of the part is not important. So you will select that you will monitor only the diameter, not the length. Okay, that is the point for the first bullet here. Okay, and then you determine where the charts should be implemented. For example, you have to implement this chart on the drilling station. Okay, and then you choose the proper type of control charts. So your data is variable data, the diameter is variable data, so you select that you will use X bar S chart. And number 4, select the data collection system. So you have to design, okay, whether you will collect the data based on manual, okay, and use the manual gauge, okay, to measure the diameter of the parts, okay, or you have like an automatic gauge, okay, you use the machine, okay, to measure the diameters, and then it will, okay, enter the data into the automatic, okay, like software that you have set up, and then it will automatically calculate the control limits, okay, and plot the control limits. Okay, you can automate the data collection system and also the analysis, the data analysis system. It depends on you, okay, whether you're going to do it automatically or in combination with manual. Okay, and 5th, okay, take action to improve the process if there is out of control pattern appear on the control charts. Okay, that is what so you have to learn about the egg test to detect the abnormality. Okay, that we will do it in a little bit later. Okay, and number 6, okay, so you have to set up form to record all the information about the process, okay, related to any changes in the process, like how much change in the machine adjustments, in what direction, the reason for any adjustment. You have to record about the batch number of the raw material, so that if there is abnormality happens, you can trace back and to see which batch, and then you can claim the supplier, okay, correctly, right? And then you have to record the operators that do the production in each lot. Okay. And the last step is to prepare the OCAP. Okay, we have seen this before, out of control action plan. Okay, it tells you the potential cost, the potential spatial cost that may happen, that may really happen, and also it will tell you the corrective action or the things that you need to do if you find the out of control pattern, so that if there's out of control point that appear, you can correct, okay, or you can solve the problem very quickly, okay. So you have to think about that in advance. Okay, so this flow charts. Okay, so what happened? Let me see. Okay, so now we have done with this, right? And the last thing that you need to do is that when to update the control limits. Okay, so actually you have to start with this concept that the control limit, okay, is based on this idea mean plus and minus 3 sigma, right? So if, okay, if you change the mean level or sigma level of your process, for example, you do machine adjustment, you find a new method, okay, to reduce the number of defectives. For example, like you change the supplier, you change the process method of machinery, okay, engineering change orders that affected the process flow. In this case, if you monitor the lead time, okay, or the production time of your process, okay, if you do something to make the production time reduce, okay, the mean, for example, the mean of the queue or the waiting time is reduced, okay, so you have to update the control limits for your waiting time, for example, okay. You improve in general, that's mean if you improve the process mean and variation, that's mean you need to update the control limits, okay. And that is the first thing. So this 3 things here, okay, corresponding to number 1 here. And the second things, okay, is that when you change the sample size, remember that, okay, for p charts, so this is equal to p bar, okay, times of p is dependent on sample size, okay. So if your sample size is changed or you decide that you will change the sample size, don't forget to update or recalculate the control limit, because your control limit should be based on the sample size that you use, okay. So this slide want to show you that every time that you change sample size or you change the process mean and variation, you have to update the control limits, okay. Okay, and in summary, after you finish with the control chart materials, so I expect that, okay, you should be able to explain the objectives of and the concept of control charts, okay, and you should be able to select the proper types of control charts. You can calculate the control limits, okay, and then you can interpret the pattern on the control charts. So now we have finished these 3 bullets, right? And then in the later part today, we will focus on how do we interpret the pattern on the control chart. Okay. Okay, now it's 10:20. Okay, so let's have a break for 15 minutes. Okay, after the break, okay, we will do the analysis based on, okay, the data in the workshop, okay. So please make sure that you download the file from Courseville, okay, and then let's meet again at 10:35, okay. So actually 15 minutes from now, okay. Okay, so do you have any questions based on the lecture that we have? Okay. Okay, if there's no question, okay, so let's meet in 15 minutes from now. See you. Okay. Okay, let's continue. Okay, in the second part here we will do workshop, okay, about the interpretation of the pattern on control chart. So everybody, let's open the file, okay, lab 1 from course wheel, and then look at the first worksheet. And we have, in this data set, we have variable data, which is the diameters of the parts. And then we collect, let's see, we should have at least 25 subgroups for calculating the control limits. And in this case, we have over 25, which is 28 subgroups. Okay, and for each subgroup, we have sample size, which is 5. Okay, 5 for each subgroup. And then we record the diameters for each part. Okay, 25, 25, 25.1, 25.11. Okay. And then we will use, suppose for each subgroup, we collect it every hour. Okay, that means our sampling frequency is 1 hour. And then we will use this data set to construct the control charts based on the formula, okay, that we have seen before. So if we do it by manual calculation, let's see. Okay, remember that. Okay, if the control limit base for X bar charts will be is X bar plus A2 times R bar, right? And X bar is an average of all data sets. We have 28 samples with 5 data points each. So we have 140 data points, right? Okay, if we average all 140 data points, we will get what we call X bar, which is the center line of the X bar charts. Okay, and UCL is equal to X bar plus A2 times R bar. So A2 is a constant based on N sample size. In this case, sample size means the number of data points for each sample, which is 5. Okay, 5 each. So we look up a table, okay, in the PowerPoint slide. Okay, I show you the table for calculating N. Okay, let's revisit that again. Okay, it's a table on page 42. Okay, so for calculation of X bar and R, we have a table. Okay, you look up at N equal to 5, and then you've got A2, okay, which is this number. This is for X bar charts. D3 and D4 is for R charts. Okay, we need D3 for LCL and D4 for UCL. Okay, and let's see. Okay, and R bar is, okay, come from this steps. So first we have to calculate the range for each subgroup. Max minus min, max is 25.1, minimum is 25. So R1 for subgroup 1 is 0.1. R for subgroup 2 is maximum is here, right? And minimum is here. So R number 2 is 0.02, okay? And then you average, okay? For 28 subgroup, you will get R bar. and then you plug in here. Okay, so now you have all the numbers, so you can get UCL, okay, and LCL. Okay, you can calculate it also. Okay, so if you do manual calculation, you have to do things like this. Okay, but now we will use a computer software called Minitab, okay, to do this calculation for you. And now let's have Pimai show you how to use Minitab to plot the control charts. Okay, Micah, please. โอเคช่วยโชว์น้องๆหน่อยค่ะ
ได้ค่ะ
So if you have Minitab, okay, you can copy the data from Excel and then paste it onto the worksheet of Minitab, okay, in column C1. Okay, and then you get what you might have right now. And then to okay พี่ไมค์ช้าๆนะคะเดี๋ยวจันพูดไปด้วยนะ so okay you will use the menu graph, okay, on the top you will see the menu, right? So you click on graph, stat or graph นะคะ
stat ค่ะ stat ค่ะ
or stat, sorry, stat, and then move to control charts, and then you select the types of control chart, which is variable charts for subgroups, okay, and then you select. In this case, I want you to do X bar with S charts, okay, with the reason that I have told you before that you can use either R or S in this case before because your sample size is less than 10. So you can use either R or S, but S is better because it uses all the data points to calculate S compared to R, which use only 2 data points, which is max and min, right? So if you use computer software, I recommend that you use S chart instead of R charts. Okay, and then you click on S. And then, okay, you select, okay, on the top part, it say that you have 2 choices to enter your data set, okay, your data. The first one is called, the data are in one column, right? Like in this case, your data points of all subgroups are in one column. Okay, so the first 5 data points belong to sample 1, right? And data number 6 to 10 belongs to sample 2. So you do it like you stack the data into one column, and then you click on data in one column. Okay, but the second format, okay, of data enter is to show the data in different columns ไม่ค่ะไม่ช่วยโชว์หน่อยว่าสมมติว่าหนูทำคอลัมน์ C3 อะค่ะ C4 ไล่ไป X1 to X5 ค่ะ okay, so you can do things like this. You will put the data, like the first row is the data from sample 1, and then you have 5 data points, right? Like you might have copy and paste it onto, okay, column C3 to C7. So this is the data, these are the data for sample 1. And then for sample 2, you copy data 6 to 10 and then paste it on the second row, okay? And if you do the data entering like this, you will click on where it says observation for a subgroup in like different columns, things like that. Okay, and then you click on, you enter column C3 to C7. Okay, and then you will have 28 rows of data corresponding to 28 samples that you have. Okay, so Pimai, you can cancel this. Okay, so if you know that there are 2 types of data entering, okay, in this case we'll use the first format. Okay, and then for the first format, it's necessary that you have to enter the subgroup size, okay, which is 5 in this case, so that it knows how do we divide the data into samples. And then you click on X by S options. Okay, and then you click on the test tab. Okay, in the test, okay, as I mentioned before, that there are 8 tests, okay, to help you to detect the abnormality on the control charts. Okay, I will explain about each test a little bit later. Okay, but here just want you to see that there are 8 rows, okay, which mean 8 tests that you can use. Okay, and on the top part, okay, if you click on the choices there, okay, you will see that you have choice to perform all the tests. Okay, so the default of Minitab, okay, it will use only one rule. I will say test or rule, okay, is the same thing. The first test is called extreme point test. Extreme point mean the point. Okay, I will show you the PowerPoint slide, okay, along to help you understand about the test. Okay, just a second. Okay, so the first test is called extreme point. That means the point which is beyond the control limits. It can be beyond in the upper part or the part below the LCL. Okay, so it means that if it appears, if you see, okay, in the second bullet that it is used with all types of control charts. That means you can use it with X chart, X bar charts, X chart, N, R charts, S charts, NP, PCU charts. Okay, all the types of charts can use this rule. Okay, and it means that the mean, okay, change from its current level, its normal level, which is the center line. Okay, let me get up first. Okay, so first we believe that when we use control charts, we believe, okay, in the beginning that the mean of our process stay at this level, which is the level of center line of the chart. Okay, but if you detect an extreme point like this, that means the mean of this process is now you believe that it shift up to this level. Okay, but if it go down, okay, you will believe that your mean shift downward, okay, to this level, and the mean shift is significant, is a lot, because it changed from the center line to the point which is over plus or minus 3 sigma, okay, of the process, right? So it's a large shift or significant shift, okay? So if this happen on X bar chart, you will say that the mean on the average of the process shift downwards significantly. But if this point is on S chart, you will say that S represents the within subgroup variation, right? The variation within the subgroup, it doesn't represent an average anymore. So if this happen on S chart, you will say that the within subgroup variation shift significantly downward. Okay. So the main point for extreme point is that it shows significant change or significant shift, okay, of the statistics that you plot. If you plot S, you will say that the within subgroup variation shift. If you plot R, it's the same thing. It shows the within subgroup variation shift. If it's on X bar chart, you will say that and there is an average shift. Okay, if you plot it on P chart, you will say that the defective rate significantly shift up, okay, like in this case. Okay, if you plot it on C chart, you will say that the number of defects shift significantly up. Okay, So it depends on the types of the chart that you use, and then the statistics that you explain will be dependent on the types of the chart that you use. Okay, that is the extreme point. And the second test is called run above, or it can be below the center line. If you have 9 consecutive points, like in this case, if you take a look at this pattern, this point, the first subgroup is below the center line, right? The second subgroup is above. So, okay, and then above continuously or consecutively, okay, for 9 points. Like this point is 1, 2, 3, 4, 5, 6, 7, 8. I'm sorry, in this example, okay, 1, 2, 3, 4, 5, 6, 7, 8. Okay, I have to tell you this. For each, for some textbooks, okay, it requires only 8 points, okay, to violate this test, okay, violate this rule. And like in this, okay, pattern, okay, it needs only 8 points. So this is the 8th point, point number 8, that is above the center line. So we will circle, okay, on the last point, or on the 8th point that is above the center line, to indicate that, okay, from this point and 7 points before it, okay, in total of 8 points are above the center line, and it's the sign that the process during this subgroup, or subgroup number 2 to number 2, 3, 4, 5, 6, 7, 8, 9, right? Subgroup number 2 to subgroup number 9, okay, represents, suppose this is an X bar chart, you will say that the subgroup number 2 to number 9 violates test number 2, which is run above center line. And it means that, or it shows that the mean of the process shift up. But if you look at the size of the mean shift, it is not that much compared to the extreme point, because the extreme point, the mean shift over 3 sigma, right? But in this case, it shift up a little bit, okay, to this level that I showed you here. Okay, the mean shift is pretty small, okay, but it's it is a strong evidence enough to say that there is a mean shift, because there are 8 points above the center line. If the mean is at this center, okay, what you expect to see is that the point should be randomly up and down, or below, above or below the center line. Okay, but in this case, if there are 8 points above the center line, okay, this is a strong enough, okay, evidence to tell us that there's a mean shift already. Okay, and you can use this rule with all types of control charts. That means you can use it with the S chart, or P chart, or C charts also. And one more thing to mention, okay, I write down 8 points here because Minitab, okay, instead of use 8 points, it requires 9 points to be able to detect, okay, with this rule. Okay, so if you use Minitab, this pattern of continuously of 8 points, okay, Minitab will not detect this pattern because it is they have only 8 points, but Minitab requires 9 points. Okay, so you can use either 8 points or 9 points, depends on you. If you do it manually or use software that you have written by yourself, so you can use 8 points. But if you use Minitab, you have to use 9 points. Okay, and the next rule is trend. Okay, trend. So if you have 6 continual in increases or decreases of points. Okay, like this. Okay, from point number 1, it decreased, right, to point number 2. And point number 3 decreases from point number 2. And it decreased continuously for 6 times. That means this is point number 1, 2, 3, 4, 5, 6, 7. 7 points here, okay, shows you 6 decreases, okay, in the statistics that you plot. In this case, okay, it can be used with all types of control charts. For example, if this is a P chart, you can say that the defective rate continuously decrease, okay, over time. Okay, if this is on S chart, you can say that the within subgroup variation continuously increase over time. Okay. Test number 4 is called cycle. So it requires 14 points alternatively up and down. Like in this case, down, up, down, up, down, up. Okay, for 14 points. So this is the 14th point. Okay, that shows this pattern. And this pattern continues to point 15. So you can circle it again, okay? But this point, no, because it's down and then it's down again. So it doesn't violate this rule anymore. So you can mark, okay, that the abnormality happens up to point 15, okay? Okay, this is test number 4, okay? Test number 5, okay, is called 2 out of 3 points in zone A or beyond. Okay, now there is zone that coming, okay, into the test. Okay, if you take a look at the picture, we will divide the areas of the control charts into 3 zones. Okay, zone A, B, and C, like in this slide. Okay, and remember that the statistics that we plot on the control charts is normally distributed like it, and it has this picture, right? This frequency, actually we call density function. Okay, and then we have a lot of high probability that we will see the points within around the average, okay, of the distribution. And then if you remember that UCL is at the place which is equal to mean plus 3 sigma, okay, and LCL is minus 3 sigma, okay. So we can divide the area, okay, in the control charts into 3 zones. Okay, let me get a pen first. Okay. So, okay, the width here, okay, it's 3 sigma from the center line and 3 sigma here also, right? Okay.
เดี๋ยวอาจารย์แชร์หน้าจอก็ได้ค่ะ
Oh, I'm sorry ค่ะมันจำไม่ได้แชร์ตั้งแต่แรกเลยนะไม่บอกกันเลยพูดตั้งหลายเทสแล้ว sorry จริงๆน้องๆยังอยู่กันไหมเนี่ยชันนินใช่ไหมชันนินอยู่ไหมยังอยู่กันไหมเนี่ยไม่มีใครทักเลยอะเวลาอาจารย์ไม่ได้แชร์หน้าจอวันหลังทักช่วยทักหน่อยนะขอโทษทีจังก็ลืมจริงๆแต่ว่าถ้าวันหลังไม่แชร์หน้าจอฝากบอกกันเลยนะมาถึง point มาถึงตรงนี้เดี๋ยว get participation กันหน่อยดีกว่าใน group number 1มีใครบ้างพวกเรารู้ชื่อกรุ๊ปกันแล้วใช่ไหมคะ
รู้ครับอาจารย์
นะคะไม่ค่อยได้ยินละค่ะฝากดังนิดนึง Okay, group 1 who are in group 1
ค่ะอาจารย์
I don't hear you. Okay พี่มายบอกได้ไหมใคร who are in group 1
ได้ค่ะแป๊บนึงนะคะ
Okay, now I will ask you some question before we move on. Okay.
group number 1 ภวัตค่ะ
ค่ะ
ภวัตสุพิชาอิสรี
Okay ภวัตสุพิชัยอิสรี Okay เอางี้ดีกว่าเดี๋ยวอาจารย์ถามนะ I'll ask you to make sure that you because I didn't show the slide when I talked about these 8 tests so I will random ask each one of you to explain about the rules before we do the workshop so start with Isari Isari could you please explain what does it mean by test number 1
Is it mean the point that it's out of the upper outside the control limit and below the control limit?
Okay, that's very good. Okay, and if this point is above or above the UCL or S chart what do you say or what do you conclude about the process?
Is it the mean shift or variation shift?
Okay, it's not mean shift because S chart, each S value represent what is represent an average or it represent other thing.
Is it other things?
Yeah, other thing. Okay, take a look at this one more time. Okay, so your data set is here, right? let me erase this first. Why can't I erase it? Okay, let's take a look at, for example, subgroup number 4. Okay, there are 5 data points for subgroup number 4. Okay, if we take an average, we call it X bar, right? But if we calculate S, which is we use this formula to calculate S, right? Remember statistics course, and N here mean 5. Each data point is Xi. Each data point is Xi. X bar is an average of this sample. So what does S represent? Start with R first. R is equal to max minus min, right? Maximum of this five data sets is 25.08 and minimum is this point, right? 24 minus 92 and is equal to 0.16, right? And then Isari, could you please answer me this question? What does R of 0.16 represent? I will help you first. It represents the difference between the maximum data point and the minimum data point, right? Or you can say, the difference mean the variation, right? Large difference mean large variation. So this shows you the variation within, right, this subgroup. Is that right?
Yes.
You get that? And then subgroup number 5, you can do the same thing. Actually up to this point you can calculate R again for subgroup number 5, and this R value shows you Oh, let me see. Okay, max is here, minimum is here, so R is equal to 0.05, and then you will see that from, sorry, it reduced from 0.16 to 0.05, okay, from subgroup number 4 to number 5, right? So if you plot it on R chart, you will see that subgroup number 4, you may get 0.16 here, and then it okay, and range shows you the variation within for each R. Okay, it tells you the variation within subgroup, right? And R chart shows you the change of the within subgroup over time. Okay, do you get what I'm saying?
Yes ค่ะ
Okay, and okay, same thing for S. Okay, if we choose to express the variation within subgroup with S statistic instead of R, because R use only 2 number, right? It neglects the 3 data points in that subgroup, right? So actually we have a choice to use another statistics called S, because S use all data points. Okay, so S is better than R. Okay, so that's why I recommend you to use S instead of R. But S show you the same thing as R represents, because okay, so it's a answer me again, please. So what does S represent?
It's like compared to R use only 2 values, but S is recommend for the data that have sample more than 10, and it use like every values in that sample space, so it's more accurate.
Yeah, very good. Okay, very good. And if R represent the within subgroup variation, okay, so what does S represent?
Is it standard deviation?
Yeah, it's the standard deviation, and it also represents the within subgroup variation also. Okay, so the within subgroup variation can be expressed by 2 indicators, R or S. You can choose either one of them. Okay, but S is better. You get that? So S also represents the variation within subgroup. Okay, and so come back. Okay, if there is suppose this is an S chart. Okay, and then you see an extreme point below the LCL. What do you conclude about this process? Okay, I'll give you one one example first. If this is on S, the variation within subgroup, right? What happened here? Okay, so if you detect this point, you will say that the within subgroup variation, okay, at this time period, okay, shift significantly downward. Okay, the point is that this is S chart, so you would say that this is the within subgroup variation that is shift. Okay, and then you tell the direction of the shift, which mean which you would say that it shift downward. Okay, and because it's extreme point, okay, the shift is significant. It moved to this point, or actually to this level. So you will say that the within subgroup variation shift significantly downward. Okay. Okay, now let's move to test number 2. Okay, test number 2. Okay, if this is on P chart, okay, P chart. Pawat, could you please help me explain the pattern here? Okay, during this period, what do you say?
ฮัลโหลครับ
Hello, ค่ะ Pawat.
ครับ
If this is on P chart, P represent what? And then could you please tell that which statistics has shift and in which direction? Okay, and talked about the size of the shift.
อาจารย์ครับพอดีเมื่อสักครู่ไม่ได้ฟังเลยครับพาร์ทนี้
ไม่ได้ฟังแล้วไปไหนมา
พอดีมีไปทำ
ไม่เป็นไรจ้ะ
โปรเจกต์
งั้นตอนนี้พร้อมฟังหรือยัง
ขอโทษครับอาจารย์
ค่ะโอเคไม่เป็นไรจ้ะแต่ว่าnext time I hope everyone like spend the time okay during the class to this class okay ไม่เป็นไรค่ะวัดnow you can listen to your friend okay and ใครอยู่เดี๋ยวอาจารย์ถามอีกคนหนึ่งในกลุ่มนี้คือใครนะเมื่อกี้มีภวัตอิสรีแล้วก็ใครอีกคนนะคะ
สุพิชาค่ะ
คะโทษนะอาจารย์ไม่ได้ยินจ้ะไม่
สุพิชาค่ะ
สุพิชา could you please help okay answer this question okay so if this is P chart so what do you conclude P represent what
is it
เดี๋ยวมันมีอะไรผิดปกติละเดี๋ยวนะอะไรค่ะเดี๋ยวขอเปิดใหม่อีกทีโอเคสุพิชาค่ะ
is P the defective rate ค่ะอาจารย์
ค่ะagain please
is P the defective rate ค่ะ
That's right. Okay, P is a defective rate. Okay, so the defective rate. Okay, you can continue.
Okay, so like พอดีเมื่อกี้อาจารย์ไม่ได้แชร์สกรีนแต่ว่าจะพยายามอธิบายเท่าที่เข้าใจอะค่ะ
โอเคโอเคถ้าอาจารย์ไม่แชร์พวกเราบอกอาจารย์ทันทีเลยนะไม่ต้องรอไม่งั้นเราจะฟังไปแล้วก็ไม่เห็นภาพสิใช่ไหมต้องบอกเลยนะคราวหลังนะโอเค
เข้าใจว่ามันเป็นปัญหาที่ฝั่งหนูคนเดียวอะค่ะอาจารย์
เหรอโอเคไม่ล่ะอาจารย์ต้องขอโทษพวกเรานั่นแหละนะแต่ว่าวันหลังช่วยกันดูถ้าไม่เห็นภาพอะไรต้องบอกเลยโอเคไม่เป็นไรค่ะ start from here now you can see the picture right โอเคไม่เป็นไรค่ะหนูดูตามรูปนี้เลยอะค่ะตามเซนส์หนูเลยโอเคนะคืออย่างนี้ start with first believe that the mean is at this level which is center line okay but now if you see 8 points okay below the center line start from here right this is below above below okay for 1 2 3 4 5 6 7 8 okay in Minitab need 9 but in this case it needs only 8 points you will see that this 8 point are continuously okay they are all below the center line okay so what does it show you about the shift in the defective rate in which direction
downward
yeah okay so you will say that the defect this pattern okay violates test number 2 from subgroup for example this is subgroup number 11 to 18 Okay, subgroup number 11 to 18 violates rule number 2, okay, which is run below center line. And this rule you can say this rule tells us that the defective rate shifts a little bit downward from its normal level. Okay, do you follow what I'm saying? Oh, so I expect you to be able to explain things like this, okay, because we will do things like this in the workshop, okay, and then you have to hand in the result of your analysis to me, and then we will have this as the our homework, okay. Homework number, I'm not sure, number 2, okay, and we have the points, okay, for the homework, okay. So you have to be you have to pay attention to your analysis here. Okay, now let's move to test number 3. Okay, trend. Okay, group 2 หรือไม่ดีกว่าไม่ช่วย random ชื่อน้องเลยค่ะให้ตอบทุกๆคนนะช่วยเชิญน้องสักคนหนึ่งแล้วช่วยอธิบายหน่อย test number 2 ค่ะ number 2 is trend. We need 6 decreases or increases of the points, and if this is on C, like decrease continuous or is significantly increased.
อาจารย์ค่ะไม่ค่อยได้ยินเสียงอาจารย์เลยอะค่ะ
เฉยสงสัยไอ้ USB หับอาจารย์มีปัญหาเด้งอยู่นะโอเคอย่างนี้ได้ยินแล้วเนาะ
ได้ยินแล้วค่ะอาจารย์
Okay, so the format of the analysis will be 3 things. First, you talk about what is changed. Second, in which direction. Third, the pattern. For example, it changed in the pattern of trend, or is significantly increased but over a short period, or it changed over a long period, like this long period. Like, but extreme point, it changed in a short period, right? And then it moved down. Okay, so please tell 3 things when you do the analysis. Okay, so now ใครนะคะพี่หมายเชิญน้องคนไหนพูดนะ
พาริสค่ะ
Paris ค่ะ Paris could you please okay analyze about this pattern
what นี่คืออะไรนะครับอาจารย์
อะไรนะคะ
what นะครับผม
what means for example if it's on X bar chart you will see that the mean of the process shift. S means the within subgroup variation. Okay, P you will say what is the defective rate that is changed. C means okay, yeah.
In my idea, I think this test can be applied to both X bar and R chart.
Actually, this test can be used with all types of control charts. You can use it for P, N, P, C, and U also. Okay, but now if you use with the C charts, okay, so what does C represent?
Center line ป่ะครับ
No. Okay, C represents defect rate. The number of defects. Okay, in the samples. Okay, so now you can say that if it's on C chart, you will say that the number of defects, okay, change. Okay. You get that? U represents what we call defect rate, because it's the number of defects over one inspection unit. So you can say defect rate. Okay, but C shows you the number of defects over n parts that you sample for each subgroup. So you can shorten it by saying that C represents the number of defects. Okay. And okay, ใครนะคนนี้โทษที
ผลิตครับ
Harit ใช่ไหม So now you know that C, okay, represent the number of defects. So let's move to the second point, in which direction that it change.
It can represent the increasing or decreasing ครับ
Yeah, I'm talking about this pattern.
In the left side is about the decreasing trend.
Yeah, so you will say that the number of defects decrease, right? Yeah. Decreasing in trend or decreasing continuously, you can say that. Okay. Okay, okay, finish just. Okay, now let's move to test number 4. Okay, number 4. So พี่นายช่วยเชิญน้องหน่อยค่ะ
สุภวิทย์ค่ะ
So Supavit, so if this is on X bar chart, what you will say?
อาจารย์ครับพอดีสุภวิทย์เขาอยู่ต่างจังหวัดอะครับเขาสัญญาณไม่ค่อยดีเลยนะ
อ๋อโอเคค่ะไม่เป็นไรค่ะงั้นคนต่อไปค่ะ
ค่ะดรพัฒน์ค่ะ
ครับ
นรพัฒน์ค่ะถ้า if this pattern happen on X bar chart, what do you conclude about this process? So if this subgroup number 1 to 14, okay, 15 here.
The 2 point that is cyclic is change in variation of the mean.
Okay, good. That will talk about the mean. Okay, so you can say, yeah, you say about the variation of the mean. Okay, that is okay too. So you, okay, let me make into, okay, I like the same conclusion, but in other words. So you will say that the mean, okay, of this process, okay, vary, okay, up and down, okay, consecutively, okay, and this show you that there is a cycle pattern happen into your process, okay, and okay, that is your conclusion. Test number 5. Okay, now we talk about zone rule. Okay, right, so let's come back to this slide. Okay, so based on normal distribution, okay, you know that this is 3 at 3 sigma, okay, minus 3 sigma, right, from center line. And if we set zone C, which is from mean plus 1 sigma to minus 1 sigma, and then zone B is from 1 sigma to 2 sigma. Okay, so you get that? And zone C actually represents 68%, okay, of the data, okay, within zone C, right? And within zone C and B, okay, it cover 95%, okay, and for plus and minus 3 sigma, it cover 99.73%. Okay, so this percentage is based on normal distribution, and then you will see that if we talk about zone C, if you plot 100 points or 100 subgroups, you expect to see about 68 subgroups that are within zone C, or it clusters around the mean, okay, closely around the mean. And the remaining, which is 32%, will be distributed within zone A and B, right? Okay. And if you take a look at this percentage, 95% minus 68, okay, which is 27, right? 20%, okay. Is that right? 20% divide in half will be 13.5%, right? This 13.5% will be the percentage that you will see, or the probability that you will see the point in zone B. That means if you plot 100 points, you will expect to see roughly about 13-14 points, okay, in zone B. And in zone A, actually is 99.73 minus 95%, right? Which is 4.73. If we divide it by 2, is about 2.3%, okay? Actually 2.4. 2.4% that you will see the point within zone A. And then you have to, we will use this probability, okay, to set up test number 5 and 6, which is test 5 is 2 out of 3 points in zone A or beyond. Beyond means zone A, for example, this pattern. This point is in zone A, right? This point is in zone B. And this point is beyond zone A. So out of 3 points, this is the first point, second point, third point. Out of these 3 points, there are 2 points, which is this point and this point, right? Which is in zone A or beyond zone A. So it violates this rule, okay? And then we can use this pattern only on X bar chart, okay? And you will conclude that from sample number, for example, 3 to 5, okay, it represents the shift in the mean of the process because this is X bar, right? So you can say that sample number 3 to 5 represents the shift up in the mean, okay, of the process. Okay, you get that? Okay, this pattern, if you see, these 2 points, okay, consecutively in zone A. So out of the 3 points here, okay, there are 2 points that are in zone A. So it represents the mean shift, okay, in downward direction. Okay, but in this pattern, actually you don't have to count this one. Okay, you don't have to consider this point. If you have 2 points that consecutively, okay, in zone A or beyond, okay, you can say that suppose this is subgroup number 10 and 11. You will say that during the time of subgroup 10 to 11, suppose it's from 10 a.m. to noon. You can say that from 10 a.m. to noon, there is a shift downward, okay, in the mean of the process. Okay. And test 6, you will use the similar concept, but you move to zone B. So zone B, you expect to see the points with higher probability than zone A, right? So you need more than 2 points. So you need 4 out of 5 points in zone B or beyond. Beyond zone B means zone A. And outside the control limits. Okay. So if you see 4 consecutive points in zone B or beyond, or from 5 points you see 4 points in zone B or beyond, you will say that the mean, okay, of the process shift up or shift down depends on the direction, okay, of the points, on the position of the points. And this test can be used only with X bar charts. You cannot use this with so sorry, this is for X bar chart. You cannot use this with RS, P, NPCU, okay, MR chart, X chart. You cannot use with other types of control charts because this rule is zone rule, so it's very sensitive to normal assumption. Actually, other statistics like variation, proportion of defective, it based on its original distribution is not normal, so we don't use with that distribution. Okay, so now let's Pimai, could you please randomly pick up one person?
นันนภัทรค่ะ
Nannapat ka. So could you please conclude what do you see, okay, from this pattern? Let me see. Okay. Okay, this is on X bar chart. What do you conclude about this?
There are small shift in the process.
Yeah, in shift in what statistics? In an average or within subgroup variation or proportion or defective. So you have to mention what parameters or statistics that it changed.
Defective.
No, it's on X bar charts. Okay. X bar represent what?
The mean of the samples.
Yeah, good. So one more time, could you make conclusion again, please?
So there are small shift in terms of the X bar in the process.
In terms of the mean, oh yeah, the mean of the process. Okay. X bar represent the mean, the population mean of the process. Okay, you say small shift because now the mean is around this level, an average of those 5 points. Okay, so the shift is about this much. Okay. So yeah, you can consider it as, yes, maybe small. And okay, that is enough for this point. Okay, and test number 7, that what is called run in zone C. Okay, zone C is within this range, and then if you see 15 consecutive point in zone C, it used only with X bar chart. Okay, you can say that abnormality happened, and this abnormality, let me talk about this first. Okay, this is the common pitfall that people make. If you take a look at this distribution, you will see that the variation of the X bar is pretty narrow, right, compared to the control limit. Okay, so somebody will think that it's a good sign. Okay, it's a good pattern because we seem to have small variation in the X bar compared to the control limits. But actually this is not true. That is because the control limit, if our control limits are correct, we should see 68% of the point within zone C, right? So that means actually the control limit should be at this level, so that you will see like 68% within this limit. Okay. So this pattern show you that the control limit is wrong. It's wrong because of, okay, because of two things. First, you do sampling method, which is called stratification. Okay, I will explain to you a little bit later. And with the combination that there are different sources of mean. Okay, so to explain about this, okay, let's take a look at okay. Okay, maybe I have to draw some picture. Suppose we have 4 machines that produce the same thing. Machine 1, machine 2, 3, 4. Okay. If, okay, we do, sorry, let me, okay, produce the same thing, okay, the same part with same spec, okay, and then if we need to take sample, okay, to plot control charts, okay, so some people may do things like this. They'll pick subgroup 1, okay, they will pick one part from each machine to be a representative of each machine. So they will take this point, this point, this point, this point, okay, from each machine, okay. And the second subgroup, okay, they will do the same thing, okay. Pick one part for each machine, okay. And if you take a look at this, if all 4 machines has the same mean, okay, 1, 2, machine 3, 4. Okay, 4 machines share the same mean, right? So this point, okay, will maybe this point from machine 1, 2, 3, 4. This point may come from here of the distribution. This point will be here. This point may come from this distribution. And if you calculate the range of this subgroup, it will be maximum minus minimum, right? So it will be this distance, right? Okay, so the method for doing sampling like this is called stratification. So stratification means you pick the part from each source, okay, equally, okay, and it's the same from samples to sample. Okay, this is called stratification. And if your mean, okay, if the mean of the the 4 machines are equal, okay, there will be no problem. You can plot, okay, you can plot the data from all machines in the same control charts. But the error happened in case that the 4 machine have different means. For example, machine number 1, 2, 3 share the same mean, like this. But machine 4 has higher mean, like this. Okay, so if you take the sample like this, okay, 1 from 1, from 2, from 3, okay, and then for machine 4, since the average is around this point, right? So the data that you collect from machine 4 will be at this level, higher level. And then when you calculate the R number, the maximum will be at this level, right? The minimum will be here. Now you will get higher range. Range in this case is higher than range in this case, right? It's higher because that there is one source of the mean that is different, right, from other sources, right? And if range, okay, if you have M subgroups, okay, the R number will be higher in case that you have different means, right? That means when you calculate UCL, your R bar will be abnormally high, okay? And A2's R bar represents the width, right, of the control limit. Because this is X bar, this is A2 R bar, UCL is at X bar plus A2 R bar, right? So A2 R bar is this distance, and this is also A2 R bar. So the width of the control limit is 2 times of A2 R bar. So if your R bar is abnormally high, the width of the control limit is abnormally wide. Is that right? So that's why you see this pattern, that is test number 7, that you will see the width of the control limit, which is too wide. So that is caused from stratification sampling in combination with different means of various source. Various source can be different machines, for example. Okay, so if this pattern happen, you observe 15 consecutive points in zone C. So you have to think about that. If there are more than one source of the mean, and then you go check, okay, if you found that you used 4 machines, okay, and you collect the data, and then you can test that whether the means of those 4 machines are equal or not using ANOVA techniques, okay. If yes, they are different, okay, and then you can at the same time, okay, you will check whether you do sampling based on stratification. If it's yes also, so that is the cause of this pattern. So what you need to do is that you need to make the mean of these 4 machines to be the same first before you share the same control charts with these machines, okay. But if you cannot make the mean of these 4 machines to be equal, that means you have to separate the control charts for each machine. Or you can use one set of control chart for machine 1, 2, and 3, which has the same level of mean. But you have to separate another control chart for machine 4, which has the different means. Do you get that? Okay, you cannot share the same control chart for the machines which have different means. Okay. Okay. We have 12 minutes left. I think we don't have enough time to do workshop, okay, in this class, okay, but we will move to the next class. But today, okay, we will spend the time to understand the rules first, and next time we will use this rule, okay, practice using this rule in the workshop, okay. So now พี่ไมค์คะช่วย pick up น้องคนหนึ่งค่ะ and okay, so the one who is picked up, please explain what do you understand from test number 7.
นักกมลค่ะ
ครับ
ค่ะ
this test this need spot the wrong control limit
ค่ะ
of the 15 consecutive point. That is zone C, because zone C need to have more than 68 in the range of 68%.
Okay, good. Okay. And what is the cost of this pattern?
I didn't hear that part because I'm go to toilet.
Oh, really? Okay. Okay, that's fine. So let's move to other people, and now you can, okay, please pay attention to what your friend will explain to you so that you understand this, okay? Okay, พี่ไมค์คะช่วย choose
นภกรค่ะ
โอเคนภกรค่ะ Okay, Napakon, could you please explain what are the causes of this pattern in test number 7?
Is a reason for this course.
ค่ะ
It's just the point that is separate from the sample, from the trend.
Could you repeat that again? Okay, let me guide you a little bit. Okay, it's written down here that it's caused by two things: stratification, sampling, and different means, okay, of various sources. So could you please explain a little bit what does it mean by stratification, sampling?
Maybe I'm not sure about the stratification. So, could you please explain again, and then I will check by myself.
Okay. Can I have like your friend explain instead? Okay. So anybody that can help in explaining what does it mean by stratification, sampling? Okay, let me explain this one more time. Okay, stratification means that you have several sources of, you can say, like production. For example, you produce this part, okay, with same spec, okay, like you have USL, okay, you have target, you have LSL for this part, okay, and then you produce it from 4 machines, let's say A, B, C, D. Okay, so these are 4 sources, okay, of your production of this part, okay, and subgroup, okay, when you take sample, okay, if you do sample like this, subgroup number 1, okay, you pick one part from machine A, one part from machine B, C, and D, and then you get sample size, which is 4, right? And subgroup 2, you repeat this exactly like 1 from A, B, C, D, okay? So you pick one part from each machine, okay? And then you have sample size equal to the number of machines. This is called stratification. Stratification. Okay. Compared to another type of sampling, which is called mixing. Okay. Suppose you have 4 machines. Okay. But you do things like this. Machine 1, machine 2, 3, and 4. Okay. You produce a part, okay, coming out of each machine. And then you put it into one, okay, maybe one bin or in one conveyor, or okay, that you mix, okay, the part into this pool, okay, so you will have many parts from, okay, all 4 machines in the same bin, okay, and then when you in the first hour, okay, hour number 1, which is subgroup 1, okay, you pick 4 parts out of this pool, and then you may get, okay, the first part may come from B, from machine B, machine A, C, D. Subgroup number 2 may come from A, C, C, D, okay? So it's not guaranteed that you repeat the same pattern like what you do in stratification, because in stratification you intend to pick up one part from each machine to compose to a subgroup. But in this method we call mixing. Mixing, that means you mix the parts from several sources of production, and then you do sampling from that pool, okay? And it's not guaranteed, okay? It's random. So the parts that you will get is random, right? This is called mixing. Okay. Now ใครนะเมื่อกี้ณภกรใช่ไหมณภกร okay, up to this point do you understand what is the difference between two sampling method, stratification and mixing?
ครับผม
Okay, and now, okay, test number 7, okay, happen when you do stratification, but with the combination that the means of these 4 machines are different. It means that at least one source of production, at least one machine has different means, okay, from other machines. Okay, and test number 8, okay, happens with, okay, the combination of mixing, sampling, and different means. Okay, and now we talked about the difference in mean, okay. As I mentioned before, okay, like this, if machine 1, 2, 3 has this level of mean, but machine number 4 has higher mean like this, okay, so, sorry, compared to the picture on the left hand side, where the means of the 4 machines are at the same level, okay, so the X, or the part that we sample, will be a little bit different, okay, from like this, and the range will be smaller than when we have different mean, because you will see that there is a high, okay, because the mean goes up, right? The X will go up also, and then this will give you the maximum, and this one will give you the minimum, and then you will get higher R bar, okay. And as I mentioned previously, that R bar represents the width, right? The width of the control limits, so that you get wider control limits, okay. And it happens if we do stratification, so for each subgroup we will have higher R bar, okay, because we guarantee that we will have mean number, machine number 4 in all subgroups, right? Okay, so the difference between stratification and mixing is that stratification, we guarantee that we will have all the source of production in each subgroup. So if machine 4 has the highest mean, it will give the maximum for all subgroups, and it guarantees that the R for each subgroup will be high, and then it guarantees that you will get high R bar. That's mean wide control limits. Okay, so when you get high control limits, you will see the pattern of run in zone C, right? But okay, if you have mixing sampling instead, okay, suppose the situation is that machine A and B, okay, has lower mean than machine C and D, okay, And if if you do mixing, sampling, and it's accidentally that you have, for example, subgroup number 4, you collect the data which compose of machine number A and B, okay, which has lower mean, higher mean, right? So the X bar of this subgroup will be low. Is that right? Because it's come from lower means. Okay. So number 5, A, B, B, C. Okay, so 2 out of 4 pass. Okay, so it tends to give you low mean. Number 6, C. Suppose you get C, C, CD, CD. Okay, so you will get higher mean, right? Okay, tends to be high. Okay, but generally you will have the mean in the middle, because okay, these 4 machines will have the same probability of being picked up, right? Okay, but so if you have mixing, sampling with different means, okay, so usually you will not see any abnormality, but it's possible also that you will have the case like this, okay, which you have low mean or high means, and the pattern that will appear on the control chart will be things like this. Okay, center line is here, right? Middle is here. But if you see 8 consecutive points that avoid zone C, like in this case, this 1, 2, 3, 4, 5, 6, 7, 8. Okay, 8 points, okay, are not in zone C. Okay, it may come from, okay, the sample that come from machine C and D or D, okay, which has higher mean, right? You will have this pattern to tell you that this indicate abnormality in sampling and in the mean level, okay, and it is caused by the different source of mean, okay, and your sampling method may be mixing, okay, and accidentally, okay, this subgroups come from the machine with higher means. Okay, and now let's take a look at this pattern. Number 1, avoid zone C, right? 2, 3, 4, 5 on the upper side, and another 6, 7, 8, another 3 on the lower side. Okay, so 5 upper plus 3 lower is 8. So 8 points, okay, avoiding zone C because there's no point in zone C at all, right? So that means, so this pattern is the pattern of avoidance of zone C also. Okay, and then it may be caused by this 5 points may come from machine A and B, which has, machine C and D, which has high mean, right? And this 3 points may come from machine A and B, which has lower means. Okay, it's possible, but it's not guaranteed that it has to happen. Okay, and if it happens, you have to think about that it may caused by mixing sampling method and or with the combination of different means situation. Okay, I'm not sure that you will get what I'm saying or not. Okay, so let's check by ask some person if you understand what I'm trying to explain here พี่ไมค์ค่ะช่วยถามน้องสักคนหน่อย
ชนินค่ะ
Okay Chanin ค่ะ Chanin could you please explain what do you understand about test number 8 avoidance of zone C Chanin ไม่ตอบอยู่เปล่างั้น move to the next person
ศิลวิทย์ค่ะ
Silawit, could you please explain what is caused what caused test number 8 avoidance of zone C okay mixing and different means what does it mean in your understanding Silawit อยู่ไหมthe next person
วนกลับมาคนเดิมแล้วค่ะอาจารย์หมดแล้ว
หมดแล้วคือไม่เป็นไรค่ะเอาคนซ้ำก็ได้ค่ะ
ได้ค่ะอิสรีค่ะ
ฮัลโหล
ค่ะอิสรีcould you please help explain what do you understand about test number 8
as I have understand that the tasting aid is causing by the mixing sampling which is like you just randomly pick and it's not like so it's not well organized so it can cause the variation to not in the zone C
so it caused avoidance of zone C because of what besides mixing sampling okay
the mixing sampling with a higher mean
actually with higher means as also lower means right two sources of mean levels okay
yes
okay that's good so okay so I think that is the time to finish this class okay so we will stop at the point that I shows you that there are 8 tests okay to detect the abnormality pattern okay on the control charts and to in summary okay 1 minute to summarize this we have 2 types okay, let me note this to you 8 tests or you can say that this is called 8 sensitivity rules okay sensitivity rules so the rules that make you more sensitive to detect abnormality and it divided into 4 and 4 rules okay so the first 4 is called non-zone rule okay which is extreme point run or below or above center line trend and cycle you do not need to divide it into zone right and these 4 rules can use for all types of control charts okay and another 4 is called zone rule okay which is rule number 5 to 8 2 out of 3 okay in zone A or beyond okay 4 out of 5 in zone B or beyond and run okay of 15 points, right, in zone C, and avoidance, okay, of 8 points of zone C, avoidance of zone C, right? And it requires zone, okay, and they are used with only X bar charts. Okay, we will not use it with RS or PCU chart. Okay, so this is the main points that you have to know. Okay, and in the next class, okay, we will practice to detect all this 8. We will use these 8 rules. Okay, to detect abnormality pattern on the control charts. Okay, so let's do workshop in the next class. And in the next class, we will learn another new content, which is the process capability analysis. Okay, and then we will do the workshop also. Okay. Okay, if you are not I suggest that, okay, you should review, okay, the content about the control charts, okay, during this week, so that in the next week, if you have any question, okay, you can ask me, okay, before we we do the workshop, okay, or you can ask me by like group, okay, or you can talk to your friends, okay, to help like explain to each other, okay, to make sure that you understand the content, okay, in regarding the control chart section before we move to other content. Okay, so at this point, do you have any questions about this class? Okay, so if not, okay, let's meet again in the next class. Okay, bye.
ขอบคุณครับ
ค่ะ
ค่ะ
ค่ะสวัสดีค่ะ อย่าลืม don't forget to do like assignments about information search. Okay, bye.